Welcome again to the second session for Business Mathematics, UGBS 202. Today we'll continue with what we started the other time on differentiation. We'll look into some other concepts where, well, we'll look at the case of increasing and decreasing nature of functions. Now, this is just a basic preamble. In business perspectives, a producer would always want to identify what points he or she would be making profits or losses. Now, if you produce a number of outputs, right? Obviously, if I were, let's say, producing some bags of rice and selling to some, at some point, diminishing returns actually does set in. With regards to production. But with regards to revenue issues too, there are certain points where you could also be making profits, and at some ranges you could start making losses. Now we can use the idea of differentiation to identify some range of values within which we could be making minimum, our profits could start dipping, or some range within which our profits could start increasing. So we want to just steal that idea from this mathematical perspective, or look at it from differentiation point of view, and then bring it, or just say, juxtapose it into the business, situation. So let's look at it from, now what we want to see here is what we call the relative extrema. Now, we're saying that, supposing I have a curve, as you can see, I have a curve with an interval a to x, or a to c. This is my x-axis and then my y-axis. Now, this is a range, right, where we have values x1, x2, x3, x4. Now, at what range is my curve increasing, or at what range is my curve reducing? Now, this case, well, I use curve because, because it's for a starter or something. But under normal circumstances, I would rather want to say a function, right? At what point is my function increasing, and at what point is it decreasing? Now, from this, just a basic rule, it says that a function f is said to be increasing on an interval, say I, when any two numbers, let's say x1 and x2, within the interval, you can have x1 being less than x2. Now, look at it this way. This is some basic stuff you can see. Supposing this is x1 and this is x2. If x1 is less than x2, then I can say at that range, my function is increasing. Now, look at it from this point of view. x1 is a point. If I draw a line tangential to this point, a straight line, you would see that the slope for that straight line would be a positive number. Why? Because the curve will be positively sloped. It's kind of going up. And so if I do the same for this, you will see that the slope at this point will be lesser than the value of the slope at this point. Now, if we have an instance like that, then within that interval, say x1 and x2, I would say my function is increasing. Let's look at the other scenario. Supposing I pick two functions. Again, let me call it, we can still use x1, x2, or let's say in my graph here, I would use x4, and let's say x3, and let's say x4. Good. Now, if a function, say f, between an interval, I, if you have x1, or let's say x3 being greater than x4, then the function we would say the function is decreasing within that interval. Now look at this. Supposing I have the slope of this function here, and then I also find the slope of this function here. Now, if the slope here happens to be greater than the slope at this point, then my function within this interval, say this point and this point, my function will be decreasing. And that's just the basic idea that we are going to adopt in calculus. Well, we're using a graph to show it now, so it looks more, let's say, nice and pretty. But let's see how we would adopt this mathematically. Now, for a range of products, you can have a number of maximum points and some number of minimum points. On this graph here, all the higher points I'll call them a maxima. And all the low points, I'll call them a minima. Let me get a pointer here. Good. So this point here is what we call a maxima. This is a minima. This is another maxima. Now think about it. If I have a number of maxima and a number of minima, then the overall or the highest point of all the maxima, I'll call it the global maxima. It's just like, say, I have 3 groups of students who take an exam. And then in all these groups, a student tops the exam. Now, in each group, we have the student who tops as the highest. And we'll call that student as the best student in that class. But if we compare all the classes, we would want to look at an overall student who tops all the entire let's say, batch of students. And so in that case here, if I compare this point to this point is a maxima. This point is also a maxima. But between this point, between these 2 points, this point here is more like the overall highest point. And so I'll call this the global maxima. And so any other point other than the overall maximum point, I'll call it the local maxima, right? Good. We'll see the essence of these points in as we move forward. Now, if I come down here as well, for this one here, I think all I have is just one minima point, and so I'll call that one again it will be my local minima and also my global minima anyway. Now, if you look at the straight lines I have here, these straight lines are tangential to the curve at that point. And so at that point, the gradient is 0. Now, if you look at a typical mathematical expression, if I took an object and I threw it up, and it gets to a certain point in the sky and starts falling, the point at which it turns from going up and comes down, at that point we say that the gradient there is 0. It's a similar assumption here. Where this flat line touches the curve here, the gradient at that point is 0. Now, what we actually do is we use this idea to identify at what point would I be gaining my highest profit, or at what point would I be making or incurring the least possible cost. Now, this is a basic, theory we apply in calculus. Now, there's just 2 conditions. If you have a function, and then you kind of differentiate the function, and then you solve for, let's say, a quantity. Now, if I find a quantity level, how sure am I that at that quantity level, I am making the highest profit? Or probably at that level, I am incurring the least cost. Now, we do 2 tests using this idea of relative minima and maxima to actually come by that decision. Now, the first is what we call the necessary condition for relative extrema. It said at the local or relative minima or maxima, or also called the relative extremum, our x prime equals 0. So it's just like saying if I have a certain function and I take the derivative of the function, that derivative is what we are referring to as what? The gradient or the slope. And so that slope is equal to what? 0. That is what this point here is trying to say. So supposing that I'm looking for the maximum quantity, and then I find a certain quantity. Whatever that quantity is, that value or that derivative there is the slope or the gradient. Now, the rule 2, however, at that point, we cannot tell whether what value or the gradient there is the highest point, or probably if it's cost, that cost is the least cost or the minimum point. And so we do the second test, which we call the sufficiency condition or the second order derivative. It is a basic something we do. After you've differentiated the first time and you've found your maximum output or your gradient, you take the second derivative of that differential. And then what you get would determine whether it is actually a maximum point or what? A minimum point. And the rule is simple. It says that if you take the second derivative of a function and then your value there, or your solution, is less than 0, then it means that that function has a relative maximum at that point. Now, if we do the otherwise, if we take the second derivative of that function, and then your function or your answer there gives you something greater than 0, then we also say that f has a relative minimum at that point, or the function has a relative minimum at that point. Now, let's try a basic, let's say, example as this one. Now, suppose that the price is given as P equals 80 minus Q over 4. Okay, so now you've been given a range between 0 and 80. Now, I just want to test between no output and a total output of 80 units. At what output level would I be probably making the highest revenue, right? Now, that is an important decision every producer would want to make. You could, well, normally we say if you want to make more profits, you produce more, you sell more. But it's not always the case where if you produce more, you're going to be making more revenue. And so we use this same idea to test for at what output level would I be making profits, my highest profits or revenue. Now it says that at what level of Q will my maximum revenue be attained. And so I take my first instance. Now, if we are looking for revenue and you've been given a function P, we know total revenue is expressed as price times quantity, isn't it? Now, if you've been given the price, what do? A basic thing is you multiply the price function by quantity. And what do you have? The total of that gives you your total revenue, right? Okay, so from my expression, 80 minus Q divided by 4, if I multiply that by Q, all I have is 80Q minus Q squared over 4. Now, if some of you are wondering how we came by this expression, this 80 minus Q over 4, again, can be rewritten as 1 over 4 into bracket 80 minus Q, right? That's a simpler expression. Right, so more like I take the 1 over 4, more like a constant, and then I put this in the bracket, and then I just multiply by the Q. And so that is why the Q doesn't affect the 4 beneath here. And so this expression here, 80Q minus Q squared divided by 4, becomes my total revenue function. Now, good. So I have my total revenue function. I want to differentiate with respect to Q. Then to find out at what quantity level would I be making my highest revenue. And so I take the differential of this expression, and then what I have is 80 minus 2Q, right? Good. Now, if I have 80 minus 2Q, the rule says that at that point, whatever I have is equal to 0. So at that point, the gradient is equal to 0. So if this is the differential of this equation, in other words, this expression here is the marginal revenue function gotten from the total revenue function. So my marginal revenue function is equal to 0. Now, if I equate this to 0, I can easily solve for Q. Is that okay? And so my Q in this case becomes 40. Now, this is from my expression or from this computation. I am trying to say that at 40 or at output level 40, I'll be making the highest revenue. But how do I know? How about 60? I am actually kind of evaluating the thing between output ranges 0 to 80. So how come if I produce 40, you're saying I'll be making the highest revenue? Well, let's test. So this is where the idea of the relative extremum or the maxima and then the minima idea comes in. And so we'll do the second test. So in fact, this is the first test. It says that we find the gradient and equate it to 0. So at the point where we find the gradient, it's equal to 0. I have done that, and you found out that your Q is 40. Let's do the sufficient condition and see whether indeed our point there is the maximum point. And so we take the second derivative. Now, if I take the second derivative of this expression, so now I have 80 minus 2Q. If I differentiated this expression the second time, this will now become minus 2, because the 80 is a constant. This one has a power of 1. I bring 1 to the front. 1 times 2, 1 times minus 2 will be minus 2. And then this one goes away. So this is what we have. See, r prime prime of q, it means that if I differentiate the revenue function the second time, what I have is minus 2. And what do you see? The rule says that if you take the second differential of the function and your value there is less than 0, it means that that is a maximum. If you actually did it and your value is greater than 0, then it is a minimum point. Okay, and so here our second differential says what? Minus 2. Indeed, minus 2 is less than 0. Therefore, 40, or when q is 40, that will be the quantity that will generate the highest revenue possible. Now, if I wanted to find out, okay, so what will be the exact amount with regards to revenue I will make, all I do is I go back to the original expression or the original function, which is this one here, right? Okay, and then I put in the function. So when I am looking for my total revenue, my original function was 80 minus, I think 80 minus 40q over 4, which is this one. Good. So when I multiplied by q, this was my total revenue function. And so what I do is I just put in the value of q into the total revenue function, and then whatever it gives me there is your revenue in actual value. And so in this case, what we are saying is if we produce at output level 40, we'll be making revenue of 400, which in other words is going to be our highest revenue. Now, if you have some time available, try some other values that are greater than 40 and see what will happen to your revenue value. You will notice that you end up getting values that are less than, let's say, 400. Right? So for instance, assume that your Q is 60, put in 60, you will find out that the value of 400, you will no longer get something that will be higher than 400. It will be something less than 400 because the right-hand side of the equation will now become bigger. And so indeed, our 40 is the highest revenue. Good. Now, let's look at another idea, which we also call the extreme value theorem. Right? Now, for the extreme value theorem, it says that if a function is continuous on a closed interval, let's say AB. Now, this is how we express a closed interval. Now, it means that in this case, we are definite. In a closed interval, we have a specific point, let's say A and B. Now, in this case, A and B are inclusive. That is why we call it a closed interval. Then the function has both a maximum value and then a minimum value, right? So let's see. Now, we should know that, one, if we want to look at this extreme value theorem, there are just two conditions we really need to consider. That the function is continuous, and then the function being analyzed is on a closed interval. So supposing I have, say, an interval as this. Let me call it A and B. Okay, so I am interested in this interval, this closed interval. Now, a maximum point could occur at this point. It could occur at this point. In fact, I could have one occurring here, here. In fact, you can have various points at which our maximum point could occur. Now, in the first instance, we did not actually consider the case of the extreme values. We considered the case of the points within the interval. But this time, on this closed interval, we want to consider this point A in addition to any other point or any other point where a maximum value could actually occur in addition to the two extremes. And that is what the idea of the extreme value theorem describes or puts across. So there's a basic rule which says, well, here we are going to do the same thing as we did before. But this time around, unlike where we are only going to find our maximum value and then do the first derivative, the second derivative test just to confirm whether it is a maximum or minimum, this time we will do our derivative test, the first derivative, equate our gradient or our slope to 0, and then find our maximum quantity. Now, after finding our maximum quantity, we will consider the maximum quantity in addition to the two extremes. Are we okay? All right, so just for like a teaser, like the question we tried solving, we were given a range of 0 to 80, and then we found a maximum value of 40, and we only tested for 40 to find our maximum value. But in this case, we are going to also consider 0, we'll consider 40, which is what we found, and then we'll also consider 80. Okay, so let's look at a practical example. Okay, so let's consider this practical example under the extreme value theorem. In fact, it is nothing different or difficult compared to what we did before. The only difference, like I said, is this time around we are going to consider the values also at the extremes of the interval we are looking at. So let's consider this example. We say a Vista TV cable company currently has 100,000 subscribers who each are paying a monthly rate of 40 cedis. A survey conducted reveals that there will be 1,000 more subscribers for each 0.25 decrease in the rate. At what rate will maximum revenue be achieved, and how many subscribers will there be at this rate? Now, just a little preamble. The question is saying that this is a TV company, but if you want to watch whatever they have for you, you would have to subscribe. And all subscribers pay 40 cedis, maybe monthly, annually, or however they do it. Now, a research currently conducted says that if the producers would offer a 0.25 decrease in the rates, then, well, they are going to have about 1,000 people jumping onto the television rate, as in subscribing. But you see, what we have to, let's say, identify here is that, now, the fact that if you just reduce that small amount, you have so many people joining or subscribing, doesn't mean that you can just keep reducing the rate until the entire nation or probably everyone is on your network. You should also understand that the more people you get, the more complicated things get, the more of the work, because you need to be doing subscriptions and attending to customer calls and lots of things. And so in this case, the TV company would want to know at what level would they actually be able to get the highest possible subscribers and also get, let's say, give their people some good money, some good value for their money. So let's try and write whatever the question is saying in some mathematical expression, and then we'll be able to put across the solution. Now, it says that the revenue is price times quantity, or the rate is going to be, or the revenue the firm would get or the company will get is going to be this rate, 40, by the total number of subscribers that the firm will have. And so, but here, we want to maximize, want to take into account what this research is saying. And so, what we want to do here is, now, supposing that we reduce our rate by 0.25, it will bring us some goodies. So let's see, so that we can actually do that kind of maximize or make use of the opportunity. So we say that let x be the number of times the rate is decreased. Now, for example, so if we decrease the rate by 0.25, now followed by, now all we are just saying is if we keep reducing the rate by 0.25 from the research, whenever we reduce by 0.25, we get 1,000 people joining our subscription. So our current rate will now be the 40 minus 0.25x. Now, x is just representing the number of people, right? The number of people who would, or the number of times that we would want to reduce the rate. Now, if we reduce it 10 times, then it's going to be whatever, it's no longer going to be 40, but 40 minus that number of times that we reduce it. And so this one gives us our rate, because we want to find the total revenue. Okay, then how about for the subscribers? Currently now we have 100,000 subscribers, Now, it says that whenever we reduce our rate by a certain amount, which is 0.25, we have 1,000 people. And so what would be the total number of subscribers, which I mean the quantity or the number? And so our 100,000, which we already have, plus 1,000x. Now, think about this way. The x here is the number of times that we are going to reduce. And so if we reduce by 5, then it means we are going to have 5,000 more people joining the train, isn't it? If we reduce by 10, then it goes on and on and on like that. And so to get our total revenue expression, what we have is, for the price, our price is going to be the 40 minus 0.25x. The x representing the number of times we intend to reduce our rate, multiplied by the quantity, which is the 100,000 plus the 1,000x. Now, the x here representing the number of times that we actually will reduce it. And it forms a perfect expression for total revenue. So now, if I expand this and distribute it, what we have now is, think 40 million plus 15,000x minus 250x squared. Now, all I did is, you take this 40, multiplied by the 100,000, take the 40 again, and multiply by 1,000x. And that is what we, and then also take this one, multiply by this, take this one, multiply by that. That is the distribution. And then group like terms, and then sum them, and you end up having this expression. Okay, so this becomes our final expression for total revenue. Okay, so let's take this expression and do the first test. It says that we take the derivative of this expression and then we equate it to 0. And so if I differentiate this, 40 million is a constant, irrespective of the size, whether it is 40 billion, 400 billion. Once it has no variable, it is a constant. And we said from the rules of differentiation, if you differentiate a constant, what happens to it? It goes away. And so if you differentiate the constant, the value is 0. Now, 15,000x. If I differentiate this, what I'm going to get is 15,000, because now I'm going to reduce this by 1, and in a number raised to the power 0 will be 1, and so it goes on like that. And how about this one? Minus 250x squared. This will become minus 500x, and I guess we all understand how. And so this becomes the derivative of the total revenue function. And here, I equate it to 0. Once I equate it to 0, I can solve for x, and my x is 30. So what I'm trying to say here is, given that our x is 30 from our solution, it means that if we reduce our subscription 30 times, we're going to be earning the highest revenue at that rate, and also have the highest, or the number of subscribers or subscriptions that we can actually manage. Now, so in this case here, from the second derivative test, we would also want to know whether indeed it is true whether if we reduce it by 30, we are actually going to have, it's actually a maximum point or something. And so if we took the second derivative of this expression, which is 15,000 minus 500x, what do we have? We will get minus 500. And minus 500 is less than 0. So indeed, that is a maximum point. Good. But because we are actually now looking at the idea of the extreme value theorem, we are not going to just end it here by evaluating our value at 30 and assume that that is the maximum. Well, maybe it is, this time, maybe it is possible that if we reduce it beyond 30, we could make more profit or not. So the extreme value theorem says that do not only evaluate this at 30, let's evaluate the entire range. Now, considering this, we said, supposing we decided not to charge anything, probably make the entire subscription free, just like multi-TV does. Well, what you would do is, here in this case, we would end up reducing it 160 times. Now, if we reduce 160 times, it means that this time it is free, right? Okay, so what we do is to get the 160, just divide 40 by 0.25, and that should be it. Okay, so here, our range is going to be 0 to 160. So what you're going to do is, if you want to find your total revenue, indeed, which of the values will give you your total revenue, you will take your R from 0, put it into the total revenue function, take R equals 30, put it into the total revenue function, and then take R equals 160 and put it again into the total revenue function. And then compare the revenues from these three computations. The one that gives you the highest would give you the total or the highest revenue. But definitely, most of the times, the maximum value would give you the highest value. But it's not always the case. In some instances, it doesn't work that way. And so here, you must try and evaluate all the options, which is the two extremes, 0 and 160, and then here. And so I tried doing it here. So I did it for 30. But we'll just take time, put 0 into this expression, do it and see what you get. Put 160 into the same expression, do it, and then put 30 into the expression. Do not put it into, well, lots of the time students kind of get confused and rather put it into the differential after they've done the differentiation. No, don't put it into this expression. Put it into the total revenue expression. In our case, we had 40 million plus 15,000x minus 250x squared. Put it into this expression, and then you find your answer. Okay, so we'll end it here for this session, and I'll meet you again for the second session.